Hello, this is a demonstration on quantum computing using IBM's quantum platform. In this presentation, we're going to cover some basics of quantum computing and then jump right into the IBM quantum platform, the installation of Qiskit, and a Hello World type tutorial in Python using our newly installed Qiskit library. So first we need to cover quantum computing and its basics so that the terminology used during the tutorial is more understandable. So quantum computing takes advantage of the principles of quantum mechanics, which involves the physics of subatomic particles. A classical computer would use bits of basic information such as like 0 or 1, but quantum computers use qubits, and these can be represented by 0, 1, or both 0 and 1 simultaneously, and that phenomena is called superposition. The benefit of quantum computing is its efficiency in solving complex problems because it can capitalize on the principles of quantum mechanics. And these are the superposition, which we just discussed, entanglement, and quantum inference. So entanglement refers to a situation where two or more qubits have a state directly related to the state of another, even if they're far apart. And quantum interference refers to the notion that quantum systems can evolve such that the probabilities of outcomes can interfere with each other, causing them to either amplify correct solutions or cancel out incorrect ones. This can make optimization and solving really large complex problems a lot more efficient than on a classical computer. Okay, so when we log into the IBM quantum platform, this is what the dashboard looks like. At the top, you can switch between the dashboard, the functions available on the platform, and then resources and workloads. Your API token will be in the right corner, and that is what you would use to call Qiskit applications on the platform in like Python. You can see your account information and your monthly usage. For the free tier, you only get 10 minutes a month, and then you can also access your recent workloads from this page. Most of the functions require a paid type subscription, but this is an example of what those might look like. So they have both application functions and they have circuit functions. So things like the optimization solver might be particularly useful for like air traffic management type problems or supply chain logistic type problems, for example. So now we're going to walk through the tutorial of how to create an IBM ID so that you can access the platform and get your API token, and then install Qiskit and perform basic operations in Python. So first we need to create an IBM ID. This process is fairly straightforward. Go to quantum.ibm.com and then follow the steps to create an IBM ID by providing the information that they ask for. And then you can log into the platform and see that API token that we saw on the previous screen. In this tutorial, we're going to use Visual Studio Code, but you can use other Python applications like Jupyter Notebook or Google Colab. I recommend Visual Studio Code because we're going to have to create an environment for Qiskit, and we want to be able to easily call that environment, and in Visual Studio Code, that's pretty straightforward. So within Visual Studio Code, you would first open a terminal window before we even begin coding, and we're going to create a localized environment. So we type conda create and then name our environment, which I named TT01. Now that we've created a local environment, we need to activate it and then install some packages. So we have to enter the following commands. So just one at a time. Conda activate TT01. Conda install pip. Pip install Qiskit. Pip install matplotlib. We need Qiskit IBM runtime. Pilotech ENC, and then Qiskit AER. Once we've gone through all of those, sometimes you'll be prompted to continue with the installation and just hit yes. Then we can start with a new Jupyter Notebook file. So we will create our, first we need to test our installation. So we'll create a test installation file. And then we need to open our new localized environment and activate it. So to do that, we're going to select the TT01 environment And to do that, in the upper right corner where we select the kernel, the activation kernel, we'll click Python environments, and then we'll click this new environment that we just created. Then we're going to go through and just import Qiskit, make sure that works, and then check the version. You can see here it says 1.2.4. And then we're going to begin a runtime service using our API token to make sure that all of that works as it should. So from Qiskit IBM runtime, we will import Qiskit runtime service, and then we'll set our service equal using this code here, and we'll put in your distinct token. It's much longer than what's shown on the screen, so just copy paste it over. And then we're going to save that to this environment using this command here, the save account, and then we'll call a backend service just to verify that that it's working. So we'll use IBM Brisbane as the service to test. And when we do that, everything works as it should. And then we can also check to see how many qubits our new backend service provides us with. Okay, so now we actually want to use Qiskit. So we're going to create a new file to go through this tutorial, and then a new IPYNB file. And then we're going to select the kernel that we selected previously that we created. So for me, that's the TT01 kernel. And then we're going to begin by creating a 2-qubit Bell state circuit. And we're going to apply a Hadamard gate to qubit 0 to create superposition. So a Hadamard gate is a fundamental gate in quantum computing, and the whole point of it is just to create that superposition so that a qubit can exist in both 0 and 1 states by transforming the qubit to have equal probabilities of being in either state. This superposition allows the quantum computer to explore multiple solutions at the same time. Once we do that, we will apply a controlled X or CNOT gate between qubits 1 and 0 to entangle them, and then we can draw the circuit with Matplotlib. So the CNOT gate is a 2-qubit quantum gate, and it flips the state of the target qubit only if the control qubit is in the 1 state. So if the control is 0, the target remains unchanged, and if the control is 1, the target qubit is flipped. So if the control qubit is 0, 0, the target qubit would be 0, 0. But if the control qubit was 1, 0, then the target qubit would be 1, 1. Next, we also need to define the poly operators as observables for measurement. These operators represent possible measurements of qubits in different bases, and poly operators are represented by a 2x2 matrix with the operators poly x, poly y, and poly z. And each of them has a unique action on a qubit associated with rotations around the x, y, and z axis of the qubit's state. So here you can see we've created our quantum circuit, applied the gates with the .h and .cx, and then we can draw our circuit and look at it here. It looks great. And then there's our poly operators that we've defined, and we've stored them in this variable called observables. Now that we have all that, we can create an estimator job that will calculate the expectation values of the quantum circuit with respect to the defined observables, and then execute the job using job.result, and then we can plot the estimation results. So here's our estimator, and when we input this code, we can first make sure that our job works correctly, and then use Matplotlib to plot the values that come from our estimator job. Now, if we want to perform the same operation but for an n-qubit circuit, we need to create a function that creates a GHZ state circuit. And a GHZ state is a special type of entangled state that involves multiple qubits, and it represents basically the maximally entangled state. So it's a combination of Hadamard gates and CNOT gates, and this is the code that we would implement in order to create that function. And then we can check it using n equals 10. So when we call our function, we get this 10-qubit circuit, and that's how we know that our function is working. So we can apply it to a much larger n, but obviously as our n gets larger, it will be more difficult to plot that. So we try it out on 10 to make sure it's working, and then we don't need to verify for larger n. And now we're going to need to define sparse poly operators, and then once we verify that these are working, we can expand our code to 100 qubit circuit. So same kind of similar functions as before, but now we're going to have, so you can see here, these were the sparse poly operators for n equals 10, so that we could check to make sure that it's working. And you can see from the results that we have all of our combinations of operators, so we're happy with that. And then we'll change n to 100 and then run the code again. This time though, we're not going to print the output because it would be massive. Now that we've done that, we need to transpile the quantum circuit for the backend IBM Brisbane, the one that we used for our test, and we're going to optimize it for execution on actual real hardware. So transpilation is the process of transforming this high-level quantum circuit to a lower-level version that helps ensure the circuit adheres to the physical limitations of the hardware being used. This process will adjust the layout of the operators to match the transpiled circuit. So this is what the code looks like to do that. And then we're going to create an estimator like we did before and store our job, but this time we're going to add some resilience options. So we're going to call resilience level, optimization level, and dynamical decoupling, and this will help mitigate noise. So when we do that, we'll run the job and then print the job ID, and then we'll store the job ID so that it's easier to call in the future. And just for information, the optimization level of 1 refers to a light optimization that minimizes the number of gates. So we could put in 0 for no optimization, or 2 and 3 for heavier optimizations. The resilience level controls the level of error mitigation that's applied during the execution process. So 0 would be low, 1 is medium, and 2 is high. And then dynamical decoupling applies additional quantum operations that help cancel out unwanted noise interactions that accumulate over time. So it basically enables a qubit to maintain its quantum state for a longer duration. Okay, now let's plot our results for this n equals 100 or 100 qubit GHZ state. And it's similar to the plotting that we've done before. And then when we run that, we get this beautiful plot here, and that's how we perform these basic operations with Qiskit.